All right, welcome everybody. Today we're going to have our final lesson about exponential functions, lesson number 33, where we talk about graphing exponential functions and about their transformations. So here's the thing, again, I know I keep talking about the AP test a lot, which remember, that of course is the goal. Just in case you've never really heard the specifics of the AP test, let me go ahead and tell you about them. You might want to write these down if you have this printed out, or even if you don't. Please make sure you're aware that next year, if you do calculus AB, which again should be everybody's goal, on the AP test, there are a total of 45 multiple choice questions. Of those 45 questions, 30 of them are without a calculator and 15 of them are with a calculator. In terms of pacing, the AP board recommends that you spend 2 minutes per question for multiple choice that is non-calculator and 3 minutes per question for multiple choice that is a calculator. And then there are also 6 free response questions, 4 of which you don't get a calculator for, 2 of which you do, and no matter what, they recommend 15 minutes per question. So again, everything I do, I'm kind of trying to get your head in the game in terms of what you're going to be expected to do next year. Obviously, you've seen a bunch of multiple choice questions, and then all these problems where I'm asking you to write and explain and justify. That is what they ask you to do in free response questions. Normally, those free response questions are worth 9 points each, which is why I've kind of tried to start showing you on a 9-point scale how you would be awarded points for those open-ended questions. So just kind of something that you want to focus on. And if you're wondering why we kind of spent so much time in this unit, it's because these are very popular types of questions for AP, things about exponential functions. Obviously, next year they would have a calc twist to them, but it's just kind of trying to help set you up for success. So in terms of graphing, again, if you were to be asked questions about exponential functions, you would likely not have your calculator available to you because at the end of the day, you could just plug it into the y equals and it really isn't that interesting. They're much more likely to already give you a graph with some equation that has letters instead of numbers and then ask you to analyze, which is what we've been doing. But at the same time, I don't want to skip where the points come from altogether. So today is going to be a relatively short lesson. Again, the first 2 pages, I already have them filled in by somebody with neater handwriting than me because I thought that you really kind of just needed to listen. It would be very simple and you could just use them as a reference. So of course, the 2 main types of functions are exponential growth and exponential decay. We've been talking about them for days. Probably the easiest function in terms of exponential growth would be 2 to the x. Of course, if you were to see f of x equals 2 to the x, that would really be 2 to the x technically plus 0. And because of that 0 in the back, that would be where the horizontal asymptote is. Remember, any other value would move the graph above or below. So if you wanted to make a quick sketch of the graph and you didn't have a graphing calculator, you normally just pick a couple of x values. A good rule of thumb when you're graphing anything, as long as the domain allows, which in this case, all real numbers, you should pick a couple negatives, definitely pick 0, and then pick a couple positives, which is why you can see that my x column is from -2 to 2. To find the corresponding y values, you're simply going to plug them into 2 to the x. So 2 to the -4, you would bring the 2 square down to the bottom, which would make it positive. So you would get 1/4, 1/2, 1, 2, and 4. Very simple. If you were to go ahead and graph those ordered pairs, you could probably very clearly see why you would get this graph that looks like exponential growth. And the truth is, if you change the base to 2.5, 2.6, 4, 5, 5.684, no matter what that base is, so long as it's greater than 1, you're going to have something that looks like growth. Obviously, the larger the base, the steeper the curve, and then there's a bunch of other transformations to consider, but that's what you want to know in general. Just to kind of bring back a couple of things here. So for this graph, please, of course, remember that the domain for any exponential is all real numbers. Remember that the range in this case here would start at the horizontal asymptote, which would be from 0 with the parentheses all the way to infinity. Let me go ahead and bring back a couple of other concepts. So I could ask you, is this exponential curve increasing or decreasing? And obviously it's increasing the whole time, which is why you would say that it's increasing from -infinity to infinity. One other concept from a couple of lessons ago is about concavity. Remember, concavity means where is the graph concave up or concave down. Concave up means that you would hold the water, where concave down means the water would spill out. And hopefully, if you were to think about putting water into this curve, you can see that it would be held the entire time. So you could further say that this graph is concave up the entire time, which would be from x equals negative infinity to x equals positive infinity. So we're always trying to kind of spiral back to old concepts. Again, nothing terribly new there, but kind of, worth a 3-minute conversation. Similarly, let's talk about decay. The most popular base for decay is 1/2 to the x. So just like before, when you are going to choose x's, as long as there's no domain restrictions, which there's not, you should generally choose a couple negative, a couple positive, and always choose 0 if possible. When you go ahead and plug that in, you can see you actually get the same values that you got for the first table, but of course they're reversed here because of the fact that it's 1/2 as opposed to being just a 2. Again, 1/2 to the x. There technically is nothing in the back, so it's technically a +0, which again is why the horizontal asymptote lives there on the axis. If you were to go ahead and plot those points, you can clearly see that you would get a curve that is exponential decay. And again, whether your base was 1/2, 1/3, 1/4, 1/100th, you're always going to get something that looks like exponential decay, and then you will either have a curve that is steeper or less steep, depending on how much closer you are to 0 as compared to 1. If we're going to go ahead and add a couple other things, just like we did up top, the domain, no matter what exponential function you have, is going to be all the real numbers. The range in this case is also 0 to infinity. If I was to ask you, where is the graph increasing or decreasing, this graph would actually be decreasing the whole time, which would be from negative infinity to infinity. And again, if you're talking about concavity, if you were talking about filling water here, I think you would agree that the water would be held the whole time. So this is an example of another graph that is concave up the whole time, which is from negative infinity to infinity. Of course, you probably remember that the concavity in a graph can change, but for exponentials, it's either one or the other. So in the first graph, you see a graph that's increasing in concave up. In the second graph here, you see a graph that's decreasing in concave up, and both of those are perfectly acceptable. So I would imagine that that is pretty straightforward. So now how can we kind of take those easy concepts and really just bring back in all those transformations that we've done year after year? So again, I have a list for you here because chances are you remember them. So number one, if you're talking about a negative on the outside, remember that's a reflection over the x-axis, and that means that the y values change their signs. That, of course, would be different than if you put a negative on the inside. That would be a y-axis reflection, which, of course, means the x would change its sign. And, of course, if you're talking about inside of an exponential function, you're talking about up in the exponent. If you were to have a big plus or minus on the outside, that's what shifts you up or down. So that is a y change. And, again, that's going to move the horizontal asymptote in this case. And then finally, if you have a change inside, that's going to shift you left and right. Remember that generally speaking, you do the opposite, although that's only true if it's a positive 1x as opposed to being anything else. That, of course, changes your x's and moves you left and right. And again, if you're talking about an exponential in particular, you would have to be up in the exponent. So if you want to kind of apply those rules, take a look below here. We are going to talk about the parent function of 2 to the x. Again, that's kind of the most typical one that we always pick. Suppose you were comparing the function of 2 to the x compared to this g function, -2 to the x plus 3 plus 2. And I was to ask you, how would it be different? So I just number my transformations to keep it straight. So first off, because of the fact that there is a negative out front, that's how I know that there's an x-axis reflection. Then up in the exponent, that x plus 3, if I were to set that equal to 0, I would get -3, which is how that I know the graph is going to shift left 3. And then that big plus 2 would, of course, mean that the graph was shifting up 2. So not only do you have to be able to write it in words, they also want you to be able to do it in terms of the coordinates. So if you had the original points and the original table on F, if you then applied these 3 transformations, how would you then be able to get a new point on G? Well, you basically want to take each of these 3 things and apply them appropriately in the correct order to the x's or the y's. So if you're talking about the x's, the only change in x is the fact that you are shifting 3 units to the left. So if you want to shift 3 units to the left, you're going to take whatever the starting x is, and you're simply going to subtract 3. That will move every point on the graph 3 units to the left. Let's say now you want to talk about what's happening to the y's. So if you want to talk about what's happening to the y's, you have to both consider the x-axis reflection and the shift. Because of order of operations, you're always going to do multiplication before any addition or subtraction, which means you're first going to make the y negative. That's the reflection, and then you're going to go up 2. So again, what am I going to be looking for you to do on a test or a quiz or an explanation? You should be able to, 1, look at the equation and describe it in words, and then you should be able to tell me how to do it with actual ordered pairs. So then just to kind of show you what they did here, I took those points that I made on the previous side for 2 to the x. I took every x value and I subtracted 3. That's how I got these right here. Then I took every y value, made it negative, and then added 2, and that's how I got these points right here. I then went ahead and took them, sketched the graph, and that, of course, gives me my graph right here. Normally, the graph, of course, with a base of 2, you would assume that that was growth, but because of the reflection, that's why it looks like decay. Where is the horizontal asymptote? Well, the horizontal asymptote comes from the big +2 on the outside. Domain is always all real numbers. Range, so underneath the horizontal asymptote, gives you -infinity to 2. Again, if we want to consider it in terms of increasing or decreasing, we would say that this graph is decreasing the whole time from -infinity to infinity. If you think about it in terms of water, if you tried to fill this with water, it would clearly be dumping out the whole time, which is why we would say that this graph is concave down from -infinity to infinity. So never a bad time to review the transformations, since they literally never go away, and never a bad idea to kind of bring back some old concepts. So 2 final problems here, just to kind of put it all together. Again, it's a relatively short lesson since we've kind of been in this discussion of exponentials for a couple of days now, and I'll give you some extra time to kind of start the homework problems. So take a look at the left-hand column, you have a g function. Take a look at the right-hand column, you have an f function. And we'll kind of look at the 2 simultaneously, just for to comparison's sake. So if you're looking at number 1 here, so g of x is 1/2 to the -x minus 2 and then -2. Explain what the changes would be if you had started with the parent function, which is 1/2 to the x, compared to on the right side, the parent function would be 2 to the x. Again, there are infinitely many parent functions for exponentials. It's whatever the base is to the x. So what are all the things that are happening here in number 1? So starting with this negative here, this of course means that it's a reflection over the y-axis. In terms of the left and right shift, because of the fact that it's a -x minus 2, you would set that equal to 0. You would get that x is equal to -2, which means left 2. And then finally, the big -2 on the outside, that would, of course, mean that you shifted down 2. Let's look at the one over here on the right. So the negative out front, that would mean that it's a reflection over the x-axis. If you look at the x minus 3 up top, x minus 3 is equal to 0. You would get x equals 3. So that's how you know that this is a shift of right 3 units. And then finally, the big -2, that's how you know that it's down 2. You don't necessarily have to number them. You could bullet them. You don't have to do any of that. Just kind of trying to keep things organized is usually a good idea. So for number 2, if you are assuming that the point xy is on the parent function, then what would you have to change it in order to make it a part of the new function? So again, this is where we're writing the coordinate rule. So how would you have to change the x's, and then how would you have to change the y's? So if we take a look over on the left-hand side here at number 1, if we're talking about the x's, we would have to take the x's and we would have to reflect them over the y-axis, and we would have to make them go left 2. And when you have those 2 things all together up in the exponent, you can really just kind of leave it as -x minus 2. So then for the y's, the only change for the y is the fact that you have to go down 2, which means you would take whatever the y value is, and you would simply subtract 2. Over on the right-hand side, if you wanted to take the points x, y, and you wanted to change them, so in terms of x's, if you're trying to take the x's and move them 3 to the right, that would be all the x values plus 3. If you were trying to reflect them over the x-axis and then go down 2, you would do the reflection first, and then you would go down 2. Okay. And again, just a note about y-axis reflections. Again, the simple transformations only work if there's a positive one in front of the x. Because that's a negative x, you're essentially factoring it out. So that's really negative x plus 2. So perhaps looking at this version makes it easier to see why it's a reflection over the y and then left 2. So all I'm doing when I write my rule here is I'm simply distributing, which you could do or not, but I just kind of want to make it clear. It's always a little bit funky when there's a y-axis transformation if there's something other than just a 1 in front of the x. So ultimately, I want to now take these rules that I've made and I just want to apply them. So if I go ahead and consider my parent tables that I already made on the other page. So here on the left side, this is 1/2 to the x. So again, -2, -1, 0, 1, 2, and that's going to be the same for both. 1/2 to the -2 gives me 4, 2, 1, half, and a fourth. And then on the right side, you get those values actually in reverse. So again, those are my parent tables, just to be clear. That's what you get if there are no transformations. And then I'm going to go ahead now and apply these rules that I made, and that's going to give me my new ordered pairs. So to find my new coordinates, so -2, 4, to change the x, -2 becomes 2 minus 2 is 0. For the y, 4 minus 2 is 2. -1 is 1 minus 2 is -1, comma, 0. And then it just takes a couple of seconds to do the rest. So -3, -1.5, and then -4, -1 and 3/4. Over on the right side, if you wanted to change the first point, -2, 1/4. So if the formula is x plus 3, so -2 plus 3 would become 1. 1/4 minus becomes -1/4, minus 2 would be -2 and a fourth. And then 2, -2.5, 3, -3, 4, -4, and 5, -6. So again, this idea of a point-by-point transformation, not a huge part of what you're going to be asked to do, again, mostly because of the fact that you're going to have graphing calculators. But again, it's worth a 15-minute lesson, which is why we're spending some time on it. And then the final step here is, of course, to go ahead and make the graph. So for each of these graphs, you're, of course, going to want to start by making sure you have the correct horizontal asymptotes. So in number 1, the horizontal asymptote would be -2, and I guess it would actually be -2 for both sides. So -2 in terms of the horizontal asymptotes. Over here on the left graph, so that would be the point 0, 2, -1, 2, -1. And again, you're really just kind of estimating. Oh, I guess it should be a little bit better than that. Okay. And then over on the right-hand graph, so you would have 5, -6, 4, -4, 3, -3, and then obviously getting closer to that horizontal asymptote. So while those steps, again, might not necessarily be new, think about all the things I can now ask you for: the domain, the range, where is it increasing or decreasing? Where is it concave up? Where is it concave down? Describe the left-handed end behavior. Describe the right-handed end behavior. Describe them in terms of whether they are bounded or unbounded. So if we're just going to do one of these, the one on the left, I would say as x goes to -infinity, you would say that g of x goes to -2. And that's an example of being bounded because it's clearly approaching just a single number. Whereas on the right side, as x goes to +infinity, you would say that g of x goes to +infinity. And that's an example of unbounded behavior because it just keeps going up and up and up with no end in sight. So again, we probably spent a little more time on this exponential stuff than we needed to, but it doesn't hurt, how hard we're going to push it here in the last couple days before winter break. So thanks very much for tuning in, guys. That's a little bit of a shorter lesson, so you have some extra time to work on homework number 33 and then to go ahead and start the review. So thanks for tuning in, and we will catch you next time.